All right, folks, let's get back at it. I think we left off on example 1 here. So let's start right there. Given the equation y equals 1/8 x squared, find dy dt if dx dt equals 3 and x equals 5. Well, let's just go first and rip through the derivative. Okay, so that's my derivative. I know that the rate of change of y with respect to time is equal to the x value at some instant divided by 4 times the rate of change of x with respect to time at that instant. Okay, so this is the derivative of y with respect to time. Now we're asked to find that value if we know these other two pieces of information. First, we know that dx dt equals 3, and second, we know that x equals 5. If we don't have those two pieces of information, we cannot answer the question about dy dt, because dx dt, well, that's one piece of information here, and then x equals 5, that's the other piece of information here. So in order to determine dy dt, we have to have those two pieces of information on the right hand side of the equation. So let's go ahead and find that value right now. Okay, so there's our answer. It's 15/4. And one way to think of that in words would be this. The y velocity at x equals 5 if the x velocity is 3. Okay, so the y velocity when x equals 5 is 15/4 if the x velocity is 3. And I'd like to show you a visual to kind of demonstrate what's going on here. So here we have the graph of y equals 1/8 x squared. I have a point on the graph. I have an x coordinate marked on the x-axis, and then the y coordinate marked on the y-axis. So as we move this point, we can see how the x and y coordinates change. But what's really more interesting is if we were to animate this thing. So let's go ahead and look. So right now I have x changing at a constant rate. Let's call that rate 3 because that's what it was in the problem. So if that constant rate equals 3, then right at the instant when x equals 5, right when x hits that point right there, right when it hits that point right there, the rate of change of y with respect to time was 15/4. You can think of that as the y velocity at that instant. So it's the rate that the y coordinate is increasing. Okay, that's a visual of what was going on in that problem. Let's take a look at another one. Given y equals cosine of x, find dy dt if dx dt equals 3 and x equals 2 pi. Same type of problem, but we have now a trig function. So let's go ahead and find the derivative. Derivative of cosine is negative sine x. Implicit differentiation. I now need to apply the chain rule. So there's my derivative of y with respect to time, negative sine x times dx dt. I'm going to evaluate this expression for the values that were given. Let me change to blue here because that's what I did in the previous one. Sure you appreciate that consistency, folks. Oh boy. There we go. dy dt equals negative times the sine, the opposite of the sine of 2 pi. That's the x value. And then I'm going to multiply by 3. Well, let's think about that. The sine of 2 pi is on the left-hand side of the unit circle. It's right on the x-axis, so that's equal to 0. 0 times 3 is 0. What does that tell us? The y velocity, this instant, is 0. So at that instant, it is not moving whatsoever. It's stationary. So let's take a look at that example graphically. We have the graph of y equals cosine x, and I'll go ahead and animate this for you. We have x increasing at a constant rate, and you'll notice the y coordinates as expected, oscillating up and down. And we were asked to find the rate of change of y with respect to time at x equals 2 pi. So right there, right at that instant when we hit the peak of that graph, the y velocity is 0. And that should contextually make sense to you because the point is going up and then it's coming back down. And right at the instant when it changes from going up to going down, its velocity is 0. Okay, there's a couple graphical examples to support the work that we did in question 1 and 2. And now for the classic related rates problem, the conical tank. This one will take a few minutes, folks, so strap yourself in. Folks, you might be wondering what you're looking at here. This is the CPU usage on my computer I'm using. So this video is getting a little long. Actually going to shut it down and start the conical tank problem on a new video.